This is a series of videos that you can come back and play again as the semester goes on. These are videos that are going to help review these objectives from Chapter 1 that you should know, but if you've forgotten them at some point, you can come back and quickly review them. So let's go ahead and get started. This first video is going to cover real numbers and some math symbols. So let's talk quickly about the real number system. There are a set of numbers that really make up real numbers. First, we're going to talk about natural numbers. Natural numbers are the numbers that we would normally start counting with, such as 1, 2, and 3. You can see them here on the number line. And then at some point, the people that were devising these sets, probably the ancient Greeks or someone in those societies, came up with whole numbers, and that was when they added the number 0 to the set of natural numbers. But natural numbers is what we normally see. Then they came up with integers. Integers were created so that we have negative numbers. Here we're looking at a number line, and we can go in the positive direction or we can go in the negative direction now with the advent of integers. These little letters over here, the N and the Z, if you were to represent these in set notation, that's the letters that we would use. But we won't have to do that, but that's what that means. We next have rational numbers. Rational numbers were developed or thought of so that we could all of a sudden represent numbers in the form of fractions, only we don't just have to represent them in the form of fractions, because all fractions can also be represented as decimals. So really, rational numbers are allowing us to represent fractions and decimals. There's just a few keys when we talk about rational numbers. For example, the number negative 1/2, I could represent this as negative 0.5. And that's also considered a rational number. Negative 0.5 is a decimal. It terminates or it ends, and that's one of the requirements to be a rational number. Or I could have, let's say I had the number 1 1/3. If I wanted to represent the number 1 1/3 as a decimal, I could write it as 1.333. And the 3's, if we did this on our calculators, would go on forever. In other words, this part of the decimal is repeating, and it is a pattern because it's always going to be 3's. So if I have a decimal that is either terminating or a repeating decimal that has a pattern, these are numbers, along with fractions, that make up the rational number system. We can move into the next set of numbers where instead of calling this, let's instead call this irrational for our purposes right now. The irrational numbers are numbers that cannot be represented as a terminating decimal, or they can't be represented as a fraction. So if I wanted to say, for example, let me pull my calculator up. Let's say I wanted to know what the square root of 2 is. So I'm going to say the square root of 2. Maybe. Oh, let's try that again. The square root, oh, I see, just a moment. 2 square root. 2 square roots is 1.4, and it's this really long decimal. It doesn't seem to form a pattern at any point, and it doesn't look like it ends. This is a representation of an irrational number. Most, all square roots that, such as 5, square root of 2, those kinds of things, when I cannot take the whole number out of the square root, these are what we consider irrational numbers. I'm going to show you this Venn diagram over here, which kind of helps also get an idea of our real number system, because as we keep adding things to our, as we keep adding numbers to our real set of real numbers, it's going to include the previous sets. For example, here I had the natural numbers. Remember, these are just our counting numbers, positive numbers. Then we added the integers. Integers make up not only the negatives but the positives. Then we added the rationals, which are the fractions or the terminating decimals. And we can have positive and negative numbers, and we can have whole numbers. So you can see that they keep, we just keep adding to our set of numbers. And this last set would be what we consider irrational numbers. Numbers that do not terminate, numbers that cannot be represented as a fraction. Pi is a really good example of that. We learned at some point in our math that pi can be represented as 3.14, and we never really had to worry about what the rest of it was, but it does go on forever. So here is just kind of a brief look of how the real number set is made up. So let's take a minute and try to pick out which numbers from this set of numbers belong to not only the whole numbers, but let's do that also for the rational numbers. Remember, the whole numbers were, and you can see I have some definitions up here. Whole numbers are the natural numbers that include the number 0. So I can scan through this set of numbers up here and I find 0. I'm only looking for whole positive numbers at this point. So I have the number 0 and I have the number 24. These are the only two numbers out of this set that belong to the whole numbers. Now let's do the same thing with rational numbers. Remember, rational numbers are going to include whole numbers, integers, fractions, decimals that terminate. So let's go through and look at this. I can't take the square root of 15 and get a whole number, so this one doesn't count. 3/4 is going to count. 24, yes, because it was part of the whole numbers a long time ago. Here I have negative 6.1 with a line over the top. Remember, the line over the top means that it is a repeating decimal, but it does form a pattern, so this would fall into my set. 0, negative 25, 7.5, and I cannot take the square root of 3 without getting a decimal, so this does not fall into my set of rational numbers. So here I ended up with 1, 2, 3, 4, 5, 6 numbers, all from the original set. Out of that set, I had 6 numbers that fell into my rational numbers concept. Okay, so that's kind of a look at the number system. Now let's quickly look at math symbols. We're familiar with equal. This symbol right here, you may have forgotten, it just means not equal to. Here we have something. We have these two symbols right here, which could be greater than or less than. Here we have less than or equal to, greater than or equal to. That's what those two symbols are. And this symbol right here, where it has 2 bars on it, would be absolute value. So let's kind of look at this. Let's say I wanted to say negative 5 is less than 3. I could come over here to my number line and I can look and see that negative 5 is right here, positive 3 is over here, and yes, indeed, negative 5 is less than positive 3. If you remember, the alligator used to eat up the big number. That's why it's facing the bigger number. Okay, what if I said 6 is greater than 1? On my number line, I would need to have a 6 out here. We'll put a 6 out here. 6 is greater than 1. Another way to read this, and the way I wrote it is 6 is greater than or equal to 1. Another way to read it, if you wanted to read from left to right, I could read 1 is less than or equal to 6. Either way you want to read that. Okay, so those are our symbols that we have over here. What about absolute value? Absolute value is really just a distance away from 0. So if I wanted to think about how far I was away from 0, that's really what absolute value means. So let's take, for example, the absolute value of -2. If -2 is right here on the number line, then I could start at 0 and I could say 1, 2. I am 2 places away from 0, so therefore the absolute value of -2 is 2. How about the absolute value of 4? Here on my number line, I know that 4 is right here. So if I wanted to say how far am I away from 0, I could say 1, 2, 3, 4. I am 4 places away from 0, so therefore the absolute value of 4 is 4. Every time you have an answer for absolute value, when you're only evaluating the absolute value, your answer will always be positive because distance is always positive. So what if I wanted to answer these questions down here? Let's look at number 1. Is the square root of 2 a rational number? Well, no. Square root of 2 is not a rational number because, like I did my calculator, when I take the square root of 2, it is a non-terminating decimal, and that makes it an irrational number. How about, is -5 an integer? Yes. -5 is an integer on the number line. If I wanted to graph -1.5 on the number line, I would draw my number line. Here I have my number line starting at -2 going up to 0. I have 10 tick marks in between. So if I graphed -1.5, I come to the -1, and then I keep going. 1, 2, 3, 4, 5. Here is -1.5 on the number line. Because we're going in the negative direction, I got to go past my -1. How about finding the value of absolute value of -6? Well, remember, if we have a number line, here is 0. Here, 1, 2, 3, 4, 5, 6 is -6, and that is 6 places. 1, 2, 3, 4, 5, 6 places away from 0, so the absolute value of -6 is 6. And how about true or false? Is -2 less than -7? Here is -2. Here is -7. If I'm going in the negative direction, this is false. Actually, -7 is less than -2. A good way to remember that is if I put your negative amounts in money terms. If I was $7 in the hole and now I'm $2 in the hole, I would really rather be $2 and not 7. So this is just a review of the set of numbers, the set of real numbers, and some of our math symbols that you're going to be using throughout this semester.